Okay, so I want to talk about tensor products of fields for a second. So tensor products of fields. All right. So I'm going to give kind of two variants. So okay. So let me just start. Okay. So so lemma. So I'm going to give a direct sum decomposition. So let k1 through km be finite extensions. So finite algebraic extensions of a field k0. All right. So all right. So then we're gonna have this. So k1 tensor up to km over k0. So we're going to have an isomorphism between this and a certain direct sum. So this is going to be a product of fields. L psi for psi in phi, okay, where phi is going to be a complete system of representatives. So phi is a subset of embeddings from ki to, so I is 1 up to m, up to the algebraic closure here, is a complete system of representatives under a certain equivalence relation, under an equivalence. Okay, and then the equivalence is given as follows. So so let's call this map here, I don't know, phi. Okay, but under the equivalence that psi 1 through psi m is equivalent to, let's say, sigma composed with psi 1, sigma composed with psi m for sigma in the absolute Galois group here. Okay, so, all right. And anything else I need to say? So okay, let me explain what these fields are. And this L psi. So this will be psi 1 k1 psi m km for psi in this thing here. And okay, and then the map here phi, and also so phi psi, I'm sorry, phi of a1 tensor up to am. So this will be psi 1 a1 psi m am, and so these vary over. So we'll get a big tuple of these, and this is what we'll call phi psi of a1 tensor up to am. Okay, and the tensor is over this field. Okay, so we have this direct sum decomposition like this. So here's another quick proof that the tensor product of fields is a direct sum of fields. So the proof is by induction. So what you can do is so for the case you could take k1 tensor km. This is a direct sum of fields. Okay, so in the case m is equal to 1, right? Then you're done. And then the inductive step, right, is that you do k1 tensor k m minus 1 tensor km. Right. This is so by inductive hypothesis, this looks like a direct sum of fi's tensor km, and this is a direct sum of fi's tensor km's, and then this is a direct sum over I, and then this is like a direct sum over j because you apply the inductive hypothesis again. Okay, so this is ji. Okay, so then that's how that proof goes. Okay, so proof. So first observe that so first the spec K1, so the tensors over K0, so this is a product of these guys, so this is a fiber product. The scheme is one-dimensional or zero-dimensional. And it's a product of fields, right? Okay. All right. So now we need to figure out what fields it is. So this product of fields is saying that this thing is a product of fields. I guess this will be a big disjoint union of fields, actually. So the idea is that each maximal ideal, right? So now, okay, so what are the fields that we're going to... So we want to break this into a direct sum of fields. And so each... okay, so how is a field given? So, each maximal ideal is the kernel of some map to a field, right? All right, so it's a kernel of a map like this. Okay, we'll write it like this. So K, some other field, but we might as well just put it in the algebraic closure. Okay, all right, and so also two embeddings will have the same kernel, so two maps have the same kernel. I shouldn't call them embeddings if they have kernels. Kernel. If and only if they differ by an automorphism. An automorphism of K0 bar. Okay, so also using the composition, right? So we have K1, so we have Ki. This goes into here. K0 bar. Each phi induces a map psi I from Ki to K0 bar, where so that and then we can write out a nice formula for this phi, so that phi of A1 tensor AM looks like psi 1 A1 psi m AM. Okay, and so yeah, and so yeah, so the idea here is that again, so that two okay, so we have, you know, that two things have the same kernel, so kernel of psi is equal to the kernel of psi prime, if and only if psi is equal to some sigma of psi prime. Okay, and so to get a complete set of ideals, maximal ideals, then we just choose right. So to get a complete set, right. So we take tuples. We take the tuples modded out by the equivalence relation. So we look at a complete system of representatives phi, a subset of here, I is equal to 1 up to m hom. So this is a k0, ki, k0 bar. Okay, and that will give us a collection of embeddings. All right. Okay, so there's another correspondence that I want to talk about. So that for primitive extensions, so embeddings and roots. So how do embeddings correspond to roots of polynomials? So I'm going to use this later. So if let's say k is equal to k0 adjoin alpha, where so we're writing it as a primitive extension, where f of x is the minimal polynomial, of alpha, then we have the following. We have that, so we have a bijection between K0 algebra maps and the set of roots, let's say beta in K0 bar with f of beta is 0. Okay? And what happens is we take some psi here, some psi 0, and it will map to psi 0 of alpha, like so. So this is with a, so here, this thing depends on a fixed primitive root here. Okay, so that's one way we have this, okay? And so, okay, so now I'm going to show something else. So let's let psi here. Okay, so what I'm going to do is I'm going to try and like kind of normalize this thing so that there's a bunch of roots, so that what these embeddings correspond to roots. So K0. Man, this is bad. My nose is kind of... Okay, so this is hom... oh, crap. Oh, man. Let's do this again. Okay, direct sum, hom, K0, K, I, K0 bar. Okay, so we're going to be a complete system of representatives. Okay, so we can normalize, and so we'll, okay, and then we're also going to let, let's say, ki is equal to k0 adjoin alpha I, where alpha I has a minimal polynomial fi. Okay, so, okay, so then we can normalize this embedding. So we can modify our phi. Okay, so let's say how we're going to modify it. So so this thing is going to be equivalent to another set of so how do we modify the phi? So so given psi 1 to psi m in phi, by changing by an automorphism, sigma in gk0 bar over k 0, we can arrange we have the following. We have that sigma 1 through sigma m is similar to the identity here on k1 psi 2 prime, psi m prime. Okay, so there's going to be some other embedding, so that this one here is going to be the identity on K. So, all right, and so such a choice of psi will be called normalized. Okay, for K1. So they'll be normalized in the first component. We can also do the normalization in other components, but I'm just going to talk about the first one because mathematically it's all the same. Okay? All right. And so given the normalized, so now, given phi, which is normalized for the first component, we have a bijection. And the bijection is as follows. So this phi here, it takes a psi, so it takes a psi 1 through psi m. Okay, and this is of course of the form, the identity on K1 and then psi m. And then it maps it to the collection of alpha prime. So this will be like alpha 2 prime, alpha m prime. All right, where f2 of alpha 2 prime, so these are other roots, right? Fm alpha m prime is equal to 0. So, okay, so the idea is that in embedding, these tuple of embeddings here, once normalized, will correspond to roots this way. And the map here is given by, we take our generator, so we specified some generators before. Where are their generators? Here, right? We specified our generators before. And then we're just going to do psi 1, alpha 1, psi m, alpha m, like so. Okay, and then this one's always going to be fixed. It's always going to be alpha 1 in the first one, because we're normalized. Okay, so this is how we get our correspondence between these two things. Okay, between the sets of roots and the sets of embeddings once they're normalized. Okay, the point of all this is that I want to give a comparison between two direct sum decompositions. Okay, so there's two direct sum decompositions. Okay, so here again we're going to be given Ki, which is going to be K0 of alpha I with polynomials Fi of x. Okay, so those are the minimal polynomials, and we're going to also be given phi a K1 normalized system of embeddings, complete system of embeddings. Okay, so they're going to be tuples of embeddings. Okay, and now what I'm going to do is I'm going to look at two things, and this is going to be applied later when I'm going to do a faithfully flat descent argument. So there's going to be this, so we're not doing QP, that's later. This doesn't matter right now what the field is. So what we're going to do is we're going to take K0 bar, okay? We're going to look at this field here, and we're going to look at K1 tensor up to Km. Okay, so if we do K0 at 1 up to Km, there's kind of two ways we can look at this. The first way was via our isomorphism. So this was isomorphic to, this was K0 bar, and then we can still tensor over K1, but now we're going to use our embedding here. Psi in phi L psi. So we use the thing that we just proved earlier. Okay. On the other hand, this thing here, this is K0 bar tensor over K1, And now we could write this like this. So this is all the other polynomials. So this will be k1 x2 up to xm, and then we mod out by f2 fm. Okay, so that's what this one looks like. And so this is actually just equal to k0 bar. So we're changing coefficients. And the benefit of going to the algebraic closure is that these polynomials now split here. So this decomposes now as a direct sum via the Chinese remainder theorem, right, as these tuples of other roots. Okay, so let me actually center this. Okay, so we're going to take tuples here of alphas. So these are the well, you'll see, of k0 bar x2 xm, and then we mod out by the maximal ideals. x2 minus alpha 2 prime xm minus alpha m prime. Okay, so we got rid of the first component and we tensored it up here. Okay, and so now what's the isomorphism between these two things? So the isomorphism between, so now what I want to describe is, okay, so we have this Chinese remainder theorem part, we have this embedding part, and we showed how embeddings correspond to roots. Okay, and so there's an isomorphism here. Okay, and this isomorphism, well, it's going to take, you know, some thing here. So this will be a tuple of x2 bar up to xm bar. The bars denote that we're looking at it in the in this equivalence class, and then we're looking at over roots here. This alpha prime vector is made up of alpha 2 up to alpha m, and those are other roots of the polynomials f. Okay, and then this thing goes to, well, what you'd expect it to go to. It goes to f of okay, now I have to do it like this, f of alpha 2 prime, alpha of m prime here, where we match up the roots and the embeddings. So here we're using the bijection here. Where's the bijection? Roots like this. So psi is going to go to psi of alpha prime. Okay, so here we're doing alpha prime because it's up to 2, like so. Oh, sorry. Sorry. We're gonna go we denote this the other way, right? So alpha prime goes to. So now, okay. So I guess we didn't want this. Also, we didn't want this one component here, right? So this should be just psi 2 alpha 2 prime. Okay, and then the map that we used before, this is alpha prime, and it goes to psi of alpha prime. Okay, that's the notation that I'm using here, right? So this this alpha prime goes to the psi of alpha prime. Okay, so there's a correspondence between these two components. That's all I wanted to say about this direct sum decomposition for now. So in the previous video, we gave a structure for tensor products of fields. We gave 2 decompositions. Now I want to talk about idempotents in tensor products of fields. Okay, in particular, I'm going to need the first one to be algebraically closed. So, or at least be the Galois hull of the other things. So let me do the lemma. So let K1 through Km be finite extensions, finite field extensions of K0 with Ki looks like Fi of Ki looks like, let me start this. So Ki is going to be a primitive extension with Ki is equal to K0 of alpha I with minimal polynomial fi. Okay, and then so if let's say that k0, let's say k1 contains the Galois closures of k2 through km, so that there's going to be so like all the polynomials split over it, then we have the following. Then k, then let's say the idempotence of k1 tensor km have the form here. So gj2 jm here, they'll look like this. So there'll be a product from j is equal to 2 up to, let's say I is equal to 2 up to m. I is 2 up to m of the following. So we'll have f, okay, so we'll write it like this: fi xi over xi minus alpha alpha I ji. Okay, so this is a j subscript I times 1 over f prime I of alpha I ji, like so. Okay, so and so here, so maybe we can write like little bars like this, and so here we're using that this thing here, tensor km, looks like k1 x2 xm modulo f2 up to fm. Okay, so this is a description of the idempotence. Okay, alternatively, so like there's one for each root. So here, okay, I don't really say what these things are. So fi, also we're using that fi of x looks like x minus alpha I 1, x minus alpha I 2, and then x minus alpha I, and then we have some degree ni, like so. Okay, alternatively, we can fix embeddings, right? Some, psi. So psi is equal to psi 1 up to psi, let's say psi 2, psi 1 up to psi m. Okay, but we'll usually fix the first one to be the identity, or we can fix any of them to be the identity. But in the proofs, we'll fix the first one to be identity, because without loss of generality, we can do the proof with the first component, and then it works for all the other ones. So alternatively, we fix some psi. So embeddings, a tuple of embeddings, psi I from ki, which is k0 alpha I, so a single alpha to k0 bar, and then here we'll use that g psi looks like the product from I is equal to 1 up to m, or I is equal to 2 up to m of f I xi. Okay, that's still in the quotient. Xi still in the quotient. Psi I alpha I 1 over f prime I psi I alpha I. Okay, so this is what we have. Okay, so this is another notation for the same thing. Okay, so the proof idea okay, so so we know that here K1 tensor K2 tensor Km. So this looks like K1 X2 XM F2 FM. This thing splits, right? So this is the direct sum over a certain size, right? And this is, or I don't know, we could write it as direct sums of alpha. Let's call this alpha primes. Okay, so these are going to be tuples of alpha 2 prime, alpha m prime. So these are going to be other roots, right, where we have K1, X2, Xm, and then we mod out by the maximal ideal. So this is just the Chinese remainder theorem, X2 minus alpha 2 prime, Xm minus alpha m prime. You know, we could do this with embeddings too. As we saw, there's a correspondence between embeddings and roots. Okay, so to find the idempotence, so finding the idempotence, is the same as solving the following. So G. So we want to. What do we want to find? So we want to find G. Solving for let's say G. Okay, we'll do it with G alpha prime, such that such that G alpha prime is congruent to 1 modulo this ideal x2 minus alpha 2 prime xm minus alpha m prime, and let's say G beta prime is equal to 0 modulo x2 minus beta 2 prime xm minus beta m prime. For alpha, this is for beta prime not equal to alpha prime, some other tuple of roots. Okay, and then we could also do this similarly with size, of course. Same thing, different notation. All right. So how do we solve for this? So we can check that this thing does the trick, right? So note that fi x over x minus alpha, let's say alpha I, alpha I prime, okay? Okay, so this is some other root, right? This approaches, so I'm gonna put this in quotes, right? So, because there's no real limit, right? But if we wanted to approach this as x approaches alpha I, right? So here, this factors completely over K1 since it's the Galois hole. And so this will just be a fact, so it'll be the degree minus 1 number of monomials here. But this thing approaches fi prime alpha I over 1 as this thing goes. So this is like L'Hopital's rule, right? Okay, but this is true even if you evaluated alpha I because it's an algebraic thing. You could also, just cancel the monomial term here and actually compute what it is, and you'll find out that it's the derivative evaluated alpha I. Anyway, so this tells us that fi of x over x minus alpha I prime times 1 over fi prime alpha I. So this thing here, let's call this G, let's call this G tilde I of x. Okay? So this thing has the property that Gi tilde, what the heck is that? Okay, so Gi tilde of alpha I is equal to 1, and Gi tilde, let's say, beta I prime is equal to 0. So for beta I, some other root, so beta I not equal to alpha I prime. Okay, so here you can see that if you plug in, this is another root, 0 here. Okay, so that's what we have. And then this, so what is this here? This is just a product of all those terms. Okay, so then to obtain a result, we just take products of the one variable version. Okay, so that's how this works. Okay, and yeah, so that's what we have. And so the remark that I guess we should make here is that so we can see that. Okay, so so there's kind of an important remark. If K0 is QP, then what can we do? So then it turns out that the different of, let's say, K over QP. Okay, so if K0 is QP, and let's say in K looks like, QP adjoint alpha, where alpha has minimal polynomial okay, actually we need a little bit more here. So if K0, so we're doing this over QP, and then we have K is a finite extension of QP with OK. So every OK can be written in this way, ZP adjoint alpha, where alpha f of x is the monic irreducible for alpha. So it's the minimal monic irreducible for alpha, right? Then this thing looks like, the different looks like f prime evaluated at alpha, right? So this is the different ideal, right, in this special case. So you can already see that in the denominators of these idempotents, right, which correspond to the direct summands of tensor products of fields once they're once there's the coefficients. So once one of them has sufficiently many roots, right, you can start to see different terms appear, right? So that's where the difference are going to come from. So it's like you're going to clear denominators to get the tensor packet of rings of integers to be the ring of to compare it with the ring of integers of the tensor packet.